Victor talked yesterday about databases on Swarm, and in general there was talk about how to write. You want to store large amounts of information that's kind of structured and searchable because we want to host websites and software as a service on Ethereum with Swarm as a backend, and all kinds of useful things. Even streaming, you want to jump to a particular place, that could be thought of as a very simple database operation of some sort. So we want to have kind of a smart system that's more than just putting files online and just downloading them and putting them back. So one way to go about it is to take an old-fashioned database like SQLite or whatever, and just apply it. If Swarm supports POSIX, as there was some discussion yesterday, then SQLite can be put on Swarm, and great. I'm claiming that there's another way possibly to go about it. And kind of the insight is that databases are really highly engineered pieces of software where the point of them is that they give you a bunch of things. They give you reliability, maintainability, synchronization, possibly distribution, redundancy, all of these great properties that on Swarm you actually get for free, right? Swarm takes care of all your data being available all the time, maintained automatically on the thing. There's no concept of splitting things among multiple hard drives, distribution. It all comes for free. So theoretically, why would we even need databases? We pay so much because databases are, I know there's database experts around here, but databases are terrible pieces of software, right? The algorithms don't make sense at all. And the reason they don't make sense is because they need to support all of these really hard tasks that in Swarm we get for free. So my point is maybe we want to design databases that are very lightweight, very efficient, and sit very nicely on Swarm just as part of the mechanism based on the API. So not in the Swarm spec itself, but on top of the API. And if you look at IPFS, this already, to some extent, is starting to happen. If you look at OrbitDB, for example. So OrbitDB is a database that was created by Had, who I think is Berlin-based. Again? Yes, Samuli. For doing a chat client, but it seems like this is happening from the bottom up, and I think there might be good reasons to do this in Swarm as well. So here are what I'm going to tell you about is something called persistent data structures. So persistent data structures is something that existed since the 80s. And these are, in one word, they were invented by Bob Tarjan, I think, and there was a bunch of work in the 80s and 90s for inventing these. And these are super, super efficient data structures that are like the data structures we know, so a way to maintain data that's kind of clean and algorithmic. It doesn't deal with complicated questions like how to keep things synced up and maintainable. Very efficient data structures that give you the ability to look at all previous editions of the data structure. So in the modern speech, the way to think about it is revision control. You can look in the past, go to the past, fork from the past, go all this. There's the partial persistence that doesn't allow you to fork from the past. There's full persistence that does. There's all of these. There's PhDs about this. So there's a whole field of study. I'll tell you a very simple persistent data structure and how to implement it on Swarm, or IPFS for that matter. So I'll tell you this in a few minutes. But the point I want to stress here is that this lives beautifully in systems like Swarm. And the reason it fits beautifully is because content addressing is almost exactly the same thing as pointer-based data structures. Right? Data structures have many, many forms. Some of them live in arrays like stacks, heaps, and some of them, but pointer-based are like this huge group of data structures that beautifully are automatically persistent. I'll show you how. It's called the fat node method if you want to Google it. So there's something called the path copying. It's on Wikipedia, so the descriptions are reasonable. And fat node method. And these live beautifully in pointer-based data structures. You get these properties for free. The reason this was originally thought to be amazing is because functional languages give you, are basically only support, or mostly only support, pointer-based data structures. So they give you any data structure that you create in functional languages has these properties for free. But guess what? Swarm and IPFS-based data structures also give you this for free, and they're also kind of functional because everything is immutable. Everything, you do content-based hash addressing, so every hash could be thought of as a pointer. And then you naturally build pointer-based data structures, and immutability comes totally for free. There's a slight point about the root. You need ENS to basically keep the root, as we've seen yesterday, because the root keeps updating. So, but except this, you get this totally for free, and it's beautiful. So let me show you a very, very simple, like the first persistent data structure that you'd see. So let's think about binary search trees. Okay? So I'm going to show kind of a very, very simple database or data structure. So binary search trees are a key value storage, right? So a dictionary that looks like this. So you have, let's say, 11. These are pointers. So in C, you'd just use them as pointers. And in Python, these would be names. And in Swarm, would be called a swarm file. Each of these nodes would be a swarm file. Or for IPFS, this I think is called a node. I should have looked it up. And for C, this would be a struct. Okay? So this is 11, 7, 15, 2, 5, 3, and 6, and so on. And every one of these 11 has a data that is associated with it. Say it's people, and this is their age, right? So there's a person here, name, and so on. Okay? Now, this is the way to store data. If you want to look for a person who's, actually, these should be IDs. These should be ID numbers, okay? If you want to look for a person whose ID is 5, you look at the root. The root was published on ENS, so it's always available. You look here, you say, oh, it's smaller. Then I go here, oh, it's, what did I do? Oh, it's larger. I go here, oh, it's 5. I found 5, and then I return this as an answer. And if it's not in the, if it's not in the data structure, you also can find it easily. You also can find that easily. So that's like a binary search tree. I think we all know it. The nice thing is let's look at what happens when you start doing updates. Okay? So suppose I want to delete 6. I chose an easy answer. What you do is you go here, you go here. You end up here. You found 6. In C, you just delete it, right? What would you do in IPFS or Swarm? You go here, you say, I want to publish a new version of this, which is the version where this points to nil. Okay? And then what you do is you actually split this node. This is called path copying. You split a new version, right? Naturally. So it's 5 now, where the old pointer, it's the same content address, right? So it's the same hash of the old thing, but it goes to nil. Then you need a new version for 4, so you copy 4, points to 5, the new 5 points to 2, then you copy 11, points to 4, points to 15, and then you have a new node in the root. And what this node does is it tells you which version you want to go to, right? If you want the version before the delete, you go left. If it's after the delete, you go right. And the way we think about it is using a time variable. So the time now, you use it clock sense epoch. Second slash epoch. So if time is more than 1,000,000, then you go right. Otherwise, you go left. That's the time of the split. Okay? You keep both of this in some central location. You have history control. You have all of the old data. How much does it cost? Very little. Why very little? Because you only copy the path to the root. So you only pay logarithmic storage. So storage, let's say there are n data items and m updates. The storage is, complexity of this whole thing is O of n plus m, and the time of all operations is O of log n plus m. under some assumptions that I'll tell you in a bit. So it's basically as efficient as the tree would be otherwise, but you get this extra revision control for free, displays beautifully inside of Swarm. This is a database that keeps updating itself. You want better data structures, you can give better data structures. Range trees that allow you to do range queries, allow you to find all the people of ages between 15 and 17 with salaries between $90,000 and $100,000, you do a range tree. You use path copying. Any possible pointer-based data structure you get for free, and it lives in Swarm beautifully, and I'm not so sure we need databases anymore.